also be taking pictures of sort of your presentation.
Perfect.
All right.
So you have to introduce yourself first.
Good evening, everyone. Some of you are actually part of the Women in Quantum group. Thank you for coming, and thank you for being a part of this lecture. I am Tiffany Linzan, and I am actually the founder of the group. For any background for those who don't know about the group, Women in Quantum was actually created from me actually having recently left IBM and being exposed to some of the stuff that they were doing in quantum computing over at Yorktown Heights. They actually have a community, it's called Qiskit, and it's actually a framework, the name of the framework that they actually use for near simulation of quantum computing. And now I do data science and data engineering, and so we're trying to work to bridge the gaps between women who are in those fields and are interested in quantum computing. Thank you.
Okay. Okay. And so I don't know if I'm focused there, so you.
Yes, I'll go ahead.
Okay. So my name is Noson Yanofsky. I teach at Brigham College, and I want to talk about quantum computing. And I'm going to talk about that Qiskit thing soon. Okay, so let's just go through it. The goal is for you to understand that first sentence. Contrary to what you probably heard, quantum computers are not faster than classical computers. So there's a big buzz about, oh, you know, quantum computers are going to change our life and things like that, and not. The power of quantum computing is that quantum algorithms, those are the programs that work on quantum computers, demand fewer operations than classical algorithms. So you can do more things. You can do things with a quantum algorithm with less operations. Okay, so we'll get to understand this. We will introduce some quantum mechanics, quantum computing, and then discuss several quantum algorithms. We move on to discuss the seeming paucity. That means how few there are of quantum algorithms, and conclude with some speculation about the future of quantum computing. So this is a little bit of intro. I don't know who I'm speaking to. I don't know what you know, and I know what some of you know, whatever, and so we're gonna hit a lot of different things, and you'll be bored by some of them. Sorry, you're one. Okay, so here's the outline of the talk: some quantum mechanics, some quantum computing, and we're gonna go through literally point by point a very simple algorithm called Deutsch's algorithm, and then we're going to talk about some other algorithms, and then we're going to ask how many quantum algorithms are there, and then we're going to talk about what happens in the world when they do make a quantum computer. So somewhere in the basement of the NSA is probably a quantum computer, and IBM probably has, you know, more than a few large, well, you can say what you want about the NSA, that's not secret, whatever. Anyways, so how will the world change with that? So we start with this. Okay, so I can't start talking about quantum mechanics without talking about the double slit experiment. And again, I'm sure you've all seen it, but it's worth it to see it again. It's Richard Feynman, and he was one of the greatest physicists of the last century, on volume 3, which is about quantum mechanics, in page 1 of 1. This, you know, can't get past this. He says, talking about the double slit experiment, we choose to examine a phenomenon which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery. And he really means that. All the other things you hear about it, it's all about this, the consequences of the double slit experiment. We cannot make the mystery go away by explaining how it works. We will just tell you how it works, okay? And so then he's talking about the double slit experiment and superposition, which we'll explain, okay? So again, I'm sure you've seen it. So if you have a light and it's going through 2 slits, but you cover over 1 slit, then you're going to have a lot of light in the center, less over here, none over here, none over there. That makes sense, okay? But if you open up both slits, then what's going to happen is the lights go through both, and there's what's called interference, thinking of light as a wave. So you're going to have some waves up and some waves down, and you're going to get some places where it's very light, some places where it's very not light, no place like that. You're going to get some type of interference thing. Now that's not strange. That's not strange at all, because thinking of light as a wave is not a bad thing. It's not a strange thing. It goes back to the time of Newton. Light can be thought of as a wave, and waves from each slit cancel each other out. The interference leads to light and dark patches. Physicists can do this experiment with one photon at a time. If this is done many times, many of the photons will land in light regions, none of the photons will land in dark regions. Question: if there's only one photon let go at a time, what does the single photon interfere with? Okay, I just want to show you the picture first. Okay, it's expected that if you let out one photon at a time, some of the photons will go there, some of the photons will go there, and you're not thinking of it as a wave. Great. But what really happens is the same type of interference pattern happens right there also, even though you're letting one photon at a time. Okay? So that's the strange thing. Again, if there's only one photon let go at a time, what does the single photon interfere with? Okay? Now, again, what is a photon? I don't know. Is it a wave? Is it not a wave? But they have ways of talking about a single photon. Okay? And the answer is the photon splits into two and interferes with itself. It does not go through either this slit or that slit. It goes through both slits at one time. Rather than saying it has position, we say it has superposition. It's in two places at one time. Okay. That's the shocking thing about quantum mechanics. Everything else is a derivative of that. And again, like Feynman said, you can't make it go away. And there are philosophers who try to think of it this way, think of it that way. It doesn't work. Okay, it's a very strange thing. Okay. Okay. In quantum mechanics, many properties not only position, it went through this slit and that slit, but other things also like spin and energy and momentum, etc., do not have a single value. Rather, they have many values. They are in a superposition. So when they are, okay, now you might say, hey, this is BS. I don't believe this. I've never seen anything in a superposition. Okay, everything seems straightforward, unless I'm drinking too much tequila, and then things kind of look like they're in a superposition. But other than that, I don't see it. And the answer is, when they are measured, they are only seen in a position. Why this happens is called the measurement problem. People argue why this happens. I have no idea why it happens. But before it is measured, it has many values. Key idea. Before measurement of an object, a property does not have a definitive value. There's no value definiteness. These are just different ways of saying the same thing. They're many different values. They're doing both at the same time. They're doing many things at the same time. There is no realism. Okay, I was getting frustrated while making this slide. You know, should I say this? Should I not say this? And again, there's a lot of people. So there's a lot of people who argue with this. You are permitted to scoff at this in disbelief. Yell out balderdash. It's being taped. I can't write any other word. Balderdash. That means, you know, balderdash. Okay? It's true anyways. Okay, so you can't get away from it. Okay, that's one thing. Another strange aspect of quantum mechanics, but again, dependent on the superposition. Superposition is the main strange thing. Another thing is entanglement. So we have to talk a little bit of background about entanglement. So subatomic particles have the ability to, they have another property called spin. And you can think of it as a spinning basketball. And the question is it spinning this way or is it spinning that way? Some particles spin, some particles don't spin. Some spin this way, some spin that way. Very nicely. Okay? Okay. And we can measure, think of the particles as spinning magnets. Okay? And what you can do is you can have a source of particles coming through here, and you have these two magnets here, and if it's spinning one way, it's going to go down this way. If it's spinning this way, it's going to go down up that way. And if it's not spinning, it's going to go across. And again, you could do this with single particles at a time and measure it and things like that. So this is called spin. It's something we don't physically see it, but we don't see the wind, but we can see the trees bend. So we can see the consequences of it. Okay? Great. Now, take a particle which does not have spin, okay? And particles break up into other particles. So you can have a particle that doesn't have spin, and it can break up into two particles that do have spin. Now, just like there's a thing of conservation of momentum, conservation of energy, conservation of mass, things like that. These are laws of physics. There's also something called conservation of spin. And the idea is as follows. You have a system. The amount of spin in the system is not going to change. So if you start off with no spin, and you break it into two particles that do have spin, then if this one is spinning positively, whatever that means, then this one must spin negatively. That's the idea of conservation of spin. They have to both spin, they have to sum up to what it started with, 0. Same thing here. If this particle, if you break off the particle and you break it up to this, and it spins this way, then the other one spins to that way. However, keep this in mind, when a particle's spinning, you take a particle that has no spin, you break it up into two, and you don't look at it. That's a key point. You're not looking at it. Before you look at it, before you measure it, it's spinning both ways. It's in a superposition. Okay? Again, not just position, but spinning. It's spinning this way, and it's spinning that way at the same time. And just as it's crazy to say it goes through this particle, goes through this slit, and goes through that slit at the same time, so too it's just as crazy and just as true to say they're spinning both at the same time. Both the same way. Okay, but here's what you can do. You can take a particle with no spin here. This is your source. You can send it this way. You can send it this way. The main thing, the main idea when entanglement's discussed is that you can send it in two different ways. This you can send to Alpha Centauri, one side of the universe. This you can send to the other side of the universe. They'll both be spinning both ways. But the key point is, when this one's measured, and let's say it's spinning positively, automatically across the universe this one's spinning negatively. Okay? And that's the phrase entanglement. These two particles are across the universe from each other, and yet when you measure one of them, it collapses to a single position. It's either spinning this way or spinning that way. And that one far away will also be spinning one way or the other. Again, hard to believe. In other words, there's no connection, there's no wire connecting this, and this is an instantaneous. It's not the speed of light or anything like that. Somehow two particles far, far apart can still be connected to each other. Now, I just want to stress how this is different than something in your real life. Okay, so, you ready? Take a dollar bill. Take two boxes, two shoe boxes. Take the dollar bill, rip the dollar bill into two, put one dollar bill in one shoebox, put another dollar bill in the other shoebox, send this shoebox to Alpha Centauri, send that shoebox to the other side of the universe. Okay, now, don't tell anybody which way, which particle is which. The person in Alpha Centauri opens the box, sees that it's the left side of the dollar bill. What does she automatically know about what's in the other box? And the answer is, well, if that's the left side, then the other person has the right side. Okay, if that's the right side, the other person has the left side. Okay, now that's standard classical world. Okay, this is different. Here, the particles, we don't look at them. We do things with our eyes closed. We put one particle in this box, one particle in that box. We close the box. Okay, then they're both spinning both ways. Both ways. You send that there, you send that there. You open the box, it collapses. It's going to be spinning one way. It collapses. You open that box over there, it's going to be spinning the other way. Okay, but the main point is, opening this box is going to have an infringement on that box. Okay, and that's a shocking thing. Okay, and again, you might say, no, the physicists are doing it wrong, and really, it's really in one of the things, and you know, after all, when you open it, it's not that it collapses, it's that it was always spinning positively. You're allowed to say that, you're wrong. This is a fact.
So I'll take your word for it, but I'm curious why the physicists think that, because in the first case with the double slit experiment, you had the rationale for saying that it went through both slits was the appearance of the interference phenomenon.
Right.
And I don't think, heard the analog of that in this spin situation. So.
Bell's theorem.
Okay.
That's the
Well, I
most.
can give a quick answer. If you could make a version of this, basically with three things where you measure. And what you find out is, you see what the probabilities are. And you find out that if you made the assumption that the thing had a definite spin state, and used the rules of probability theory, you would not be able to compute the values that you actually measure when you do the experiment.
Right. Anyways, that's Bell's theorem. Okay. Okay, great. We're now finished quantum here. I just want to point out, if you are interested more about quantum mechanics, I wrote a book called The Outer Limits of Reason, What Science, Mathematics, and Logic Cannot Tell Us. It's a great book. You're welcome to look at it. Anyways, it has a whole chapter on quantum mechanics for, it's without equations or anything like that. Let's talk about quantum computing. Okay, so let's first talk about regular computing. Regular computing, your bit is either 0 or 1. And by 0 or 1, I mean switch on, switch off. Electricity going this way, electricity going that way, electricity going through a transistor, electricity not. We can make a more interesting bit, we might call it a probabilistic bit, where something's a little bit on, a little bit off. And so you can talk about things that are halfway true and halfway false. For example, if you're standing in the doorway, are you in the room or not in the room? Things like that. But a quantum bit has a whole range of possible values. And to get into this, we have to talk about complex numbers, and I don't want to get into complex numbers, but basically a quantum bit has, not only could it be 0 or 1, it could be a whole range of different things. Okay? And the whole range is described by complex numbers. A bit, let's read. So here we're talking about the states of the system. Just like when we talk about a computer, we can talk about where are the computers up to, and then later on we're going to talk about dynamics. How do you change the information? What does a computer do? It takes bits and it manipulates them, it changes them. Okay? So too, a quantum computer is going to take qubits and it's going to manipulate them. And we're going to see how. So a bit is either 0 or 1. Switches on or off, electricity flowing or not flowing through a transistor, a metal ring magnetized one way or another way. A qubit is C0, that's a complex number, don't have to know about it, in the state 0, plus C1 in the state 1. C0, now what that does is it says, look, I don't want something that's either 0 or 1, I want something that's both 0 or 1. Okay? And which one will it be? Well, these numbers, these C0 and the C1, these complex numbers will tell you which one it will be. Okay? So what they do is they tell you the number that you're going to get, the probability of the value you're going to get when you look at it, when you measure it. So again, things are in a superposition, they're in a haze, they're here and there. Okay? But then you look at it and it collapses. Well, which one is it going to collapse? Is it going to collapse to 0 or is it going to collapse to 1? These complex numbers tell you that. So C0 tells you the chances that after measuring the qubit it will be found in 0. C1 tells you the chance that it will be found in 1. Okay? And so these two numbers also have to get along because you want, probability of this and the probability of that, but you don't want any other probabilities, so you want to make sure that these numbers have some mathematics that get along. Great. That's with 1 bit. How about 2 bits? Well, when you look at 2 qubits and you measure them, what possibilities do you have? Well, you can have them both in 0, you can have 0 and 1, you can have 1 and 0, you can have 1 and 1. Okay, again, whenever you look at something, it becomes classical, it becomes a bit. So, there are 4 possibilities. So, in order to describe 2 qubits, you're going to have 4 numbers, 4 complex numbers. C00, C01, C10, C11. These numbers are going to tell you what's the probability that it's going to collapse to this particular thing. So we get these 4 things. The main point I want you to get is, for 1 bit you need 2 numbers. For 2 qubits you need 4 numbers. For a system with n qubits, there are 2 to the n possible values that can be found after measurement. In other words, if I take n qubits and I look at them, I'm going to get 0, 1, 1, 0, 1, 1, 1, 1, 0, etc., etc. There are 2 to the n possible things I can look at, and therefore I'm going to need 2 to the n possible numbers. To describe, so now let's go back classically. To describe n bits, you need n bits. I want to describe n bits, I say, okay, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1. That's it, I describe n bits. But if I want to describe qubits before they're collapsed, okay, I need 2 to the n complex numbers. Okay, and this is where quantum computers get interesting, because this exponential growth was one of the first ideas that got Feynman interested in making quantum computers. Feynman said, if you want to mimic quantum computers, you better have a quantum, if you want to mimic quantum systems, you better have a quantum computer. He realized that you need too many numbers to describe a quantum system. You need exponential amount of complex numbers to describe it. And so if you want to describe, and this is back in the 80s, 1980s, he says if you want to describe some type of quantum system, you better have a quantum computer that can do that. And so he was the first, one of the first people to do it. There's a few other people. Okay, so let's talk about it. Why can't we just mimic a computer, a quantum computer with a regular computer? Every modern computer has at least 64 bits. Imagine a 64-qubit computer. That would demand million, billion, trillion, a lot more complex numbers. Hence, it is impossible to mimic a large quantum computer with a regular computer. You need a quantum computer to do quantum systems, not a classical computer. Okay? And it's all this thing about, because when I look at it, I have 2 to the n possibilities, so too, that's why, because when I look at it, I have 2 to the n possibility, that's why I need 2 to the n possible numbers to describe each one of those possibilities. Okay? So, mimicking a large-scale quantum computer is not going to work. You can't do that. Okay, great. Now, that's the states. Now I want to talk about how quantum computers change. So let's go through it. Basically, the idea is as follows. You're going to have these qubits, and then you're going to manipulate the qubits, okay, and do strange things with them until you get what you want. So let's go back a little bit. In a regular computer, bits are manipulated by logic gates. This little computer in here has 1 million little logic gates, and they're doing all types of mean and nasty things to your bits. ORs, NORs, etc., etc. You take those gates and you build up nice little circuits. And these are essentially programs. This is what a program is. You have the inputs here, they're doing these things, da-da-da, and the output is over there. Very nice. That's what a computer program is all about. Well, we're going to have the exact same thing over here. Great. In a quantum computer, qubits are manipulated by quantum gates, not logical circuits, but quantum gates. A quantum program is going to be a composition of quantum gates. I think I have a nice picture. Hold on. It's going to be something like that. Don't get nervous. Okay? But it's going to be the same thing. We're going to put in our qubits, our bits here. We're going to make them qubits. They're going to be qubits. Da, 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 da. We're going to measure them over here. We're going to get out real answers over there. Same type of thing. The same ideology goes through the same way. Okay? So there's nothing really mysterious about quantum computers. Just like classical computers take bits, use logical gates, get out results, compose the logical gates, so too quantum computers take bits, do quantum gates to them, measure them at the end, and get out things. Let's go back over there. Let's go through it. Usually we're going to start by putting qubits in a superposition. Okay? So the main idea of quantum computing is as follows. Let's say I'm searching for something. Rather than doing it like a classical computer where I search for this, search over here, search over there, search over there, search over there, search over there, go into a superposition at one time and try everything at the same time. That's the slight intuition of what a quantum computer is all about. So I'm going to start by putting qubits in a superposition. Then we're going to manipulate them with quantum gates. At the end, we measure them, because at the end, the results we want to know are real live results. And one more thing. The reason why it's so hard to make a quantum computer is that it's hard to make sure that we are not measuring the qubits and they stay in a superposition. Let me explain what I mean. Okay? We go into a superposition. Well, you better make sure that you're not measuring them here, because what happens when you measure a qubit? It becomes a bit. That becomes uninteresting, like these things, computers. Okay? So you better make sure that they're not measured. That's the whole hardship of physically making a quantum computer. You want to keep that superposition going as long as you can. Okay, good. Okay. Quantum gates come in two forms. We can measure things, so that's one of the things you do. You have a superposition and you simply measure it. You look at it, you measure how much things it does. Okay, another thing you could do is what's called unitary or reversible operators. You can manipulate the qubit. It can be in some superposition. You can change the superposition this way or that way. We're going to do not a lot of them, so we'll get that. So here's an example. This is called a Hadamard gate, and it does the following. This is a very important one. If you enter a 0 into it, into the Hadamard gate, it automatically goes a little bit to the 0 and a little bit to the 1. It's like it puts you halfway there, halfway 0 and halfway 1. That's the center core of computers. I said, if you want to do something quantumly, try doing them all at one time. So you need that Hadamard gate. The Hadamard gate is going to be an important gate. Okay? Now, there's a lot of other gates, and I'm not getting into them, but one of them is function evaluation. Let me just say what that means. Let's say I have a function that takes inputs and puts out outputs. Okay? To be thought of as a black box, you don't know what's going on, but you put the input here and you put the output there. Okay? Now, that's a great thing. The only thing is, this has a problem, because I told you that all universal operators, they have to be reversible. And it's not clear that this function can, you can reverse it. In other words, you can undo what it does. You can get out the information. Okay, so this is one of the technical details. We're not going to go into this about quantum, these gates, is that they have to be reversible. Whatever you do one way, you have to be able to undo. Okay, that's not going to work because I'm losing information. I can't get my X back in. Okay? But we have a way of dealing with that. And that's this. This is called a real function evaluation. It goes as follows. You have two inputs. One input is what you really want to evaluate, X, and I want to evaluate and get out f of X. That's one thing. And the other thing you really want is, this is what's called the control bit. And the control says, do I want it yes or no? Okay, the Y is 0, 1. Do I want to give the real answer yes or no? Or I can give the inverse thing. The point of this is, this gate with these two inputs and these two outputs are reversible. The input, you can get the output from the input. I just want to give you an example. Addition is not a reversible operation. 5 plus 2 is equal to 7. Now if you get out that 7, you don't know what the input is. Could have been 3 plus 4, could have been 6 plus 1, could have been 7 plus 0. Okay? So addition is not a reversible operation. Quantum computers are limited. They can only deal with reversible operations. Okay. This way of dealing with this is the right way of dealing with it. Okay? Notice the input becomes part of the output. You're giving already half the information. Okay? And so you're going to get something like that. Okay. Anyways, we're going to use these three operations to do a real algorithm. Okay? I got 25 minutes to tell you what a real algorithm is. Okay. There are many others, and we're not going into them. Okay, great. Now, I just want to tell you, and this is what you were talking about, you can actually do this. IBM has a way of actually, and as far as I know, I thought it was, you said simulated. I didn't use the word simulated. They have a publicly available 5-qubit computer that you can actually try. Okay? And it's, as far as I know, it's not simulated. What you do is you pick, here's your 5 qubits, 1, 2, 3, 4, 5. You take the gates that you want and you click and push. And again, I'm not explaining what all these gates are. Notice these are the measuring gates at the end. These are the operators you're dealing with and different things. And you could save them, and then you can simulate it, I guess, and then but you can also run it. And IBM lets you do this, and it's exactly the same thing as I was doing. Okay? You have the 5 qubits, you put in the operations the way you want, and you want to see what the results are at the end. And maybe we could talk about more afterwards, how it works or what it's doing. But this is a real thing. Okay? The only thing is, 5 qubits is not very big. It means the biggest number you can factor is 32. Well, I can factor. But anyways, it's publicly available and quite interesting and a little bit fun also. Okay, great. So let's talk about a real algorithm. Okay, so the first algorithm is Deutsch's algorithm. Hold on. This book will change your life. Quantum Computing for Computer Scientists. Okay, and it has a lot on these things, and this is where I'm getting the stuff. And we're passing it around.
I do actually own this, by the way.
See, and her life is better because of that. And so will your nieces and nephews and friends be. Anyways, so that book. I need that copy back. I got 10 free copies when I finished the book, and my mother took 9 of them. So that's my only copy. She had to show everybody that. You see, I told you he wasn't an idiot. Okay, great. So let's talk about Deutsch's algorithm. It's a simple algorithm. It's a simple little problem, and it's very clever, and it shows all of these. Okay, Deutsch's algorithm deals with a function. F takes 0, 1. It takes a bit, and it outputs 0, 1. Now, there are 4 types of functions like that take a bit and output a bit. Okay, and we're going to go through them. Okay, the problem asks whether f is constant. In other words, f of 0 is equal to f of 1, or balanced. F of 0 is not equal to f of 1. Okay, so you have a function, and you want to know yes or no. Is it constant? Does it go like this, or does it go like that? Okay, and now let's go through the possibility. Classically, this demands 2 function evaluations. Let's go through. You start off, you know no information whatsoever. You evaluate f of 0, you can get out either f of 0 is equal to 0 or 1. You get some information. Then, you do a second function evaluation, and you get f of 1 is equal to 0, or you evaluate 1. Okay? Now look here. If f of 0 is 0 and f of 1 is 0, it's a constant function. If f of 0 is 1 and f of 1 is 1, you get a constant function. Here, you get mixed. 0, 1, 1, 0. Those are balanced. Great. Let's go back up. Classically, this demands 2 function evaluations. Question, how can you do it with a quantum? With a quantum computer, this problem can be solved with 1 function evaluation. Now that's an amazing thing. Okay, and that's the smallest type of quantum algorithm you can have. And we can kind of figure out how it works. Okay, basically, instead of evaluating it at 0, or evaluating it at 1, what do you evaluate it? On a superposition of 0 and 1. Try plugging into f both 0 and 1 at the same time. Now, it's not going to work, but that's the intuition. Okay? We're going to show you what works in a minute. So here's the first stab. You ready? You have your function evaluation. Put the input, rather than doing the input at 0, you put the input at a Hadamard gate. You first do a Hadamard gate, which makes it into a superposition of both. Then try that, and then at the end measure it. Now that's a good idea. That's a good starting point. It doesn't work. We have to get into, and she's going to yell at me if I go till 8 o'clock. I want to go through this for hours and hours, but I'm not going to. So we're going to go through this a little bit quickly, and you're going to borrow the book if you want. Well, you're going to buy the book if you want. Okay, so here's another possibility, and this doesn't work either, is take this H, take this control bit, and try controlling it halfway 0, halfway 1, or both 0 and 1 at the same time. Okay? And again, put in whatever x you want, put this control bit, and again, we didn't really have a clear intuition of what this control bit is, and then do the function evaluation, and then measure it. Okay? That doesn't work either, okay? But this does work. Okay? And what you do is, you put the input into a Hadamard gate, and both 0 and 1 at the same time. You also put the control gate in at the same time. And then when you're finished, you put the output again in a Hadamard gate, and you do both of them, and you measure at the top. And it turns out, again, the intuition is the same. Namely, you're trying both inputs at the same time, but you need a little bit more extra thing, because you have to understand what this control gate is all about and what it's for. But that works, okay? And again, we can go through, notice here, I have what each state is. The states start off as 0, 1. Then the states are over here, then the states are here. I'm writing what the states of the position is. This is like, for computer people, this is like a screen dumps. What do they call them? Not screen dumps. Yeah, screen dumps.
A trace of your...
Trace of the program, right. Not screen dumps.
Core dump?
Core dumps. Core dumps. Yeah. These are core dumps along the way. Okay, great. I just want to show you why this is not magic. Okay? This function f has two pieces of information. What the value is at 0, what the value is at 1. Okay. Now, I showed you the previous way of looking at it, but you can look at it a different way. You can say, look, I don't have any information. I want to know, is it constant or balanced? Now, once you find out, let's say it's constant, then you could do another function evaluation and say f of 0 is 0. Now, if you know the function's constant and f of 0 is 0, you automatically know that f of 1 is 0, right? That gives you all the information. If you know it's constant and you know that the input gives you 0, then f of 1 is also. If you know it's balanced and f of 0 is 0, balanced means the opposite. You're going to have f of 1 is 1. Okay? So what this thing is really doing is it's changing the type of question you can ask. Okay? And that's what's going on, and I call it a change of basis. The f function has 2 bits of information. Usually we need 2 bits of information to determine if it's balanced to constant. That was that last slide that I showed you in the beginning. But we can change the basis of the question and find out the information another way. And so we can get out those 2 bits of information another way. With one function evaluation, we do constant and balanced, and then we get that out. Okay, great. Let's talk about other algorithms. I'm not going to show how they work. I just want to show you what the other algorithms do. Okay? One is called the Deutsch-Jose algorithm. It's a generalization of that algorithm. And it says, look, I have not one input, but I have a string of zeros and ones, and n strings. This function, I have this function like that takes this string of zeros and ones and outputs 0 and 1. And I'm told that it's either constant, that means no matter what input you have, automatically it's either 0 or 1. It's always constant, the function's always constant, or balanced. What do I mean by balanced? I have 2 to the n inputs. There are 2 to the n strings of 0 and 1s. Okay? Well, 2 to the n minus 1, in other words, half of them go to 0, and half of them go to 1. Okay, so I'm given this function, and I'm told it's either constant or balanced. Okay? Guess what? And my question is, the problem is to determine if it's constant or balanced. Okay, so now let's think as a classical programmer, a regular computer person. Classically, this demands, what do you have to do regularly? Well, I plug in an input. If it's 0, that's fine. I plug in another input. If it's 1, I now know what? One input is 0, one input is 1. It's a balanced function. Okay, but let's say I plug in an input, it's 0. I plug in another input, it's 0. I plug in another input, it's 0. I plug in another input, it's 0. When do I know that it's constant and not balanced? Well, when I do more than half of the possible inputs, again, either half of them are constant, all of them go to 1, or exactly half of them go to one input and the other go to the other. So again, if I plug in a lot of inputs and I get out the same outputs, I still don't know that it's constant. I have to go more than half, one more than half. Great. That's how long it takes to do classically. Ready? What about a quantum computer? With a quantum computer, this can be done with one function evaluation. Exactly one function evaluation. And the way it's done, exactly the way you think it's done. You go into a superposition of all of them. It's a generalization of the thing. You go into a superposition of all 2 to the n possible inputs. You do something with the control bits, the same nonsense with the control bits, and you get out with one function evaluation. That's an amazing thing. That's a super speed up also. That's not speed up from 2 function evaluations to 1. That's from exponential function evaluations to 1 function evaluation. That's an exponential speed up, but it's not a typical problem. It's not a problem that shows up very often. And we're going to have that problem a lot. Problems don't show up. Okay, I'm going to go through this one a little bit fast because it's not very, doesn't show up that often, but it's part of Simon's periodicity function. We have a function that accepts strings of zeros and ones and outputs strings of zeros and ones. Okay, but they're periodic, which means f of x is equal to y. The outputs are the same thing. The periodic means it goes in some type of period. F of x is equal to f of y if and only if x equals to y plus c. So eventually they do this. Okay, the problem is to find c, find the period, find how long, how often it goes like that. Okay, classically this demands 2 to the n minus 1 function evaluations. With a quantum computer this can be done with n function evaluations. Again, we're not getting into it. This is not an interesting, well, this is not important. Okay. The next 2 algorithms are very important. This one is called Grover's search algorithm. It goes as follows. You're dealing with a function, many inputs, strings of zeros and ones, okay, going to 0 and 1, where we are assured, promised, that there is exactly one x, member of here, there's one input, such that f of x is equal to 1. Okay? We are required to find the x. Okay, this is called searching for a pin in a haystack. Okay? You have what's a pin in a haystack? You have one pin in a giant haystack. You have to find one of them. Okay? And that's Grover's algorithm. And this is Grover's algorithm. Okay? Now, classically, you have to try all possibilities until you find the one you want. Classically, this demands you have 2 to the n inputs. It could be that the last hay you look at is the pin. So you have to try all 2 to the n function evaluations. To try all of them. With a quantum computer, this can be done in 2 to the n over 2, or the square root of 2 to the n function evaluations. That's very good, but it's not an exponential speedup. It's a very good speedup. I wrote very important because most of the quantum algorithms that we use are using this. You want to find something very quickly, or you want to find something quickly, you use a Grover's algorithm to find it in much less time. But again, it's still exponential. In a classical computer, it's exponential. In a quantum computer, it's exponential. Most quantum algorithms use this algorithm. Notice the speedup does not take an exponential problem to a polynomial problem. It doesn't help. Okay, great. And now, this is the most important one. Shor's factoring algorithm factors a whole number in a polynomial time. Given a whole number, okay, factor it. Find the factors. This is not, there is no known polynomial algorithm that does this with a classical computer. Okay, takes more than just polynomial time to factor. This algorithm was described in 1994 by Peter Shor, and this will destroy RSA. Okay? When they make a real quantum computer, this will destroy RSA, and you won't be able to buy anything over Amazon, and the world will end. Not really. Okay, and that's what, okay, what about other quantum quantum algorithms? Not much more. There's not much more quantum algorithms than that. Okay, and it's not only me saying that. How many quantum algorithms are there? Here's a paper by Peter Shor. Now he came out with his Shor's algorithm in 1994. This paper is 2003, and he asked the following question: why haven't more quantum algorithms been found? That's a simple question. And again, that's 16 years old. Now, I don't know what he would say now. Maybe he would say that there are a lot of quantum algorithms. I've looked around. There's not a lot of quantum algorithms. There's not a lot of quantum algorithms. There's a 4-page paper. It's available online. Shor offers 2 possible answers. One, we simply do not have the intuition for quantum algorithms yet. We simply don't know how to do quantum algorithms very well. We don't have that intuition of put things in a superposition. We do have classical algorithms, and so that's why it doesn't. Another thing he says, and this is more interesting, there are few problems for which quantum algorithms can be successfully used. Okay? Now, we will spend the rest of this talk understanding the second answer. I want to explain to you what that means. Not why it's true, but just what it means that we don't have a lot of algorithms. But notice, without more quantum algorithms, all the efforts to build quantum computers is for naught. You can have all the quantum computers, you can sit there with all the engineers who I love and respect for years and years and let them build wonderful things. If you don't have good algorithms, it's for naught, it's for nothing. Okay? And yet, there are not a lot of algorithms. Okay, so let's talk about the post-quantum world. So one of the things I want to tell you is that the world will not end when the NSA comes out with their computer in their basement and tells you that they've been reading what you've been ordering from Amazon.com. Okay? So one of the ways I want to tell you that is because there's a lot of hard problems that computers can't solve, that computers have a hard time solving. And one of them is the traveling salesman problem. So I want to spend 5 minutes telling you what the traveling salesman problem is. Traveling salesperson. Okay, a traveling salesman wants to visit some cities, and obviously, wrong, bad. Okay, X. And he wants the shortest path that hits every city exactly once. He wants to go to a bunch of cities, and he wants to do this so that he hits every single city exactly once. Here's a nice little typical way of doing it. I specifically did it not in the right way. In other words, I would put New York over here, Miami goes down here, Los Angeles, whatever. But this gives you all the distances between all these different cities. And there are 6 cities here, 1, 2, 3, 4, 5, 6. And my question the question is, I want to visit every one of these cities exactly once. I want to come back to the original place where I started, and I want to do it for the shortest amount of distance, or the shortest amount of price, whatever. Okay? And I want the computer to find out what the shortest thing is. So let's see, how would you do it as a programmer? Well, a traveling salesman, we did that already. Okay? For 6 cities, it's very simple. You try all different possibilities. You have 6 possibilities for the first city, 5 possibilities for the second city, 4 possibilities for the third city. Because you have 6 factorial different possible routes. What you do is take every possible route, add up all the numbers, make sure you go back home, okay? Add up the numbers and look for the minimum number. Very simple. Okay? Go through all 6 factorial possibilities. For each one, add up all the numbers and find the shortest. And it's not hard because there are only 720 possible routes. And this computer here can do about 1 million possible routes in a second. So this will take you microseconds flat to solve this problem for 6 cities. How about for n cities? Okay? Let's say I want to go to the n most populous cities in the United States, the 100 most populous cities in the United States. I want to spend 3 days in each city, keep on traveling, selling my widgets to whoever, and then going to the next city, and I want to do it in the shortest possible amount. So how do I do that? Well, let's try, or not how do I do it, we do it the same way, but how long will it take to calculate what the shortest possible route is? So I try n is equal to 100. Again, for 6 cities, this computer will be finished in a second flat. Question, for 100 cities, how long will it take? Any guesses? Venture a guess.
A lot longer than this talk.
But this talk is over in 5 minutes, under penalty.
Google years.
Google years. How long will it
No, it can't be Google because that's 100. I have 100 there.
How long will it take?
Age of the universe.
Age of the universe. That's pretty good. Most people say 2 weeks. Age of the universe is okay. Okay, so let's calculate. 100 factorial. That's 100 factorial. Okay? The main point is, every time you multiply by 100, you're adding 2 digits. Multiply by 99, you're adding 2 digits. Multiply by 98, you're adding 2 digits. So you're adding a lot of 2 digits there. Okay. Now, question, how long does it take? Well, if you have a computer that checks 1 million paths, possible routes in a second, then we need 100 factorial divided by 1 million seconds. Right? Well, that's how many seconds. Divided by 60, you get that many minutes. Divided by 60 gets that many hours. Divided by 24 gets that many days. Divided by 365 gets that many years. Divided by 100 gets 2.9 times 10 to the 142 centuries. Okay, so it's longer than the universe, for sure. Okay, longer than a Google whatever.
Only a little bit, though.
Right. Anyways, that's a hell of a long time. Okay, and by the way, I could have asked the question, I wanted to visit 300 cities. Okay, that's going to be not 10 times larger than that, but much, much worse than that. So this is an essential limitation to our ability to know. That's why I wrote this book. I'm talking about limitations of what you can know. Okay, great. So it plays a major role here. This is something, it has an objective answer. There is a shortest path. Okay, it has a yes, it has an objective answer, and yet and a computer can do it. It just will die of heat death beforehand. Okay, responses to the TSP. Responses to the traveling salesman pattern. Whenever I teach this, I always get, first of all, I always get Fowler. Yeah, because you don't use Apple. My Mac. I always get some student in the class saying, you know, that's because you're still using Steve Gates, you know, whatever. But anyways, no, that's not true. Okay, it's a big problem. The other responses I get is, look, you're right, my computer can't solve it. This computer can't solve it because it can only solve 1 million paths in a second. But how about if we had a computer that did 10 billion paths in a second? Okay? So I would wait, and I have to say, in my own lifetime, computers have gone from when I had my TI-99, beautiful computer, till I have this, till I have my computer that I have now. Computers have gone 10,000 times faster. So it's not strange to wait for a computer that can go 10,000 times faster. I promise you in 10 years you're going to have computers that go 10,000 times faster. Okay? Computers that go 10,000 times, well, that'll only take you 2.9 times 10 to the 137 centuries. That's 10,000, 1/10,000 of 10 to the 142 centuries. Okay? That's not helping you much. Okay, that's not helping you much. Faster computers are not helping you too much. Okay, what about putting it up on the cloud and getting an internet? Everybody should go on the internet and download part of the problem and solve some of the problem. Okay, you can have 10,000 processors working at the same time, and again, 1/10,000 of 10 to the 142 is 10 to the 137 centuries. It's not helping you much. Okay, you can have all the processors you want. It's not going to help. This is just a sidebar. Physicists tell us that there are 10 to the 80 particles in the universe. If every particle in the universe was a computer, then it will only take 10 to the 62 centuries to solve. Okay? Every particle in the universe is not a computer working on your problem. However, that's not going to really help you. Okay? Great. What about quantum computers? Okay? That's the main point of this. What about quantum computers? Well, you can use Grover's algorithm. We have a Grover's algorithm, can search through all n factorial, and it'll only take, instead of 10 to the 71 centuries, 10 to the 142, it'll take 10 to the 71 centuries. Again, it's not helping. Quantum computers are not going to help you solve the traveling salesman problem. Okay? So don't get nervous about, oh, the NSA is going to break into RSA and then we'll never be able to send secret messages on computers again, because there will always be harder messages. Okay? And there will always be harder problems, and this is what's called post-quantum cryptography. There's already a whole field about this, post-quantum cryptography. Cryptography that deals with, let's say there is a quantum computer and we can have, large-scale quantum computers. Anyways, main point, there's always a lot of harder problems. There are very hard problems even for quantum computers. Great. There is a way of getting around the traveling salesman problem, and this is just a little bit of a sidebar. What about finding a better algorithm? Rather than looking at every single possible route, do some type of manipulation of the data and find a clever way of doing it. Okay? There has been a search for an improved algorithm for almost 50 years, to no avail. No one's found it. It probably does not exist, but no one has proved that it doesn't exist. So we're looking for a better algorithm, but a lot of people have been looking for a better algorithm, and they haven't found it. Finding a polynomial algorithm or proving that none exist would solve the P equals NP problem. That's a hard computer problem. Again, it's been around for about 50 years. You can make $1 million if you solve it. You can make $5 million if you solve it. You can make $6 million if you solve it. Let me just tell you quickly how to make $6 million. So in the year 2000, there were the 7 millennial problems. Okay, 7 millennial problems. These are hard math problems that you can, if you solve any of them, you get $1 million. Okay, only one has been solved so far. Something called the Poincare conjecture has been solved. The guy who solved it didn't want the money. He also didn't want to give it to me. Sad. Okay. However, if you solve the P is equal to NP problem, you can not only get $1 million, well, if you solve it one way, namely if you show that P is equal to NP, you can not only get $1 million for that, but you can plug in all the other problems, formally put them into a computer, look for a proof of them, and you can solve all of them. So you can get $6 million. If you think you know how to do it, come over and tell me first. We'll talk. No, just kidding. Traveling salesman is an example of a large class of problems called NP-complete problems, for which there does not seem to be any helpful polynomial quantum algorithms. Okay? Quantum algorithms are not going to help you with NP-complete problems like the traveling salesman. Great. So here's what we have. Okay? These are called NP problems. These are the problems that most people work with. Okay? P stands for polynomial. That means we have regular programs to do that. And we have a lot of such problems. Okay? Most computer science majors spend their entire life learning how to do problems here. Addition, multiplication, sorting, testing whether or not something is a prime number, linear programming, tens of thousands of more. This is what computer scientists spend their time doing, dealing with such problems. Very easy problems. Doable problems. Okay? As opposed to that, we have very hard problems. One of them I showed you, but they're all pretty much equivalently hard. Traveling salesman problem, something called the Hamiltonian path problem, subset sum problem, knapsack problem, satisfiability, that's about logic. Okay? Thousands more of these very, very hard problems that a quantum computer can't help you with. We're left with things in here. Okay? And we showed you factoring. That's what Shor's algorithm is all about. He showed you that. He showed you that there's a quantum algorithm for that. So again, quantum algorithms are not very interesting here. Quantum algorithms are impossible here. There are some quantum algorithms here. You ready? factoring, discrete log problem, whatever that is. That's Mr. Shor also did. Okay. Now there's another problem in here called graph isomorphism. Okay. Let me show you what graph isomorphism is. Take these two graphs. Okay. Question: are they isomorphic? Are they the same picture? Are they really the same picture, just manipulating? Answer: yes, they are. Okay, and the colors show you the isomorphism. So, given two graphs, determine if they are the same, and yes, they are. This is a problem that's in here. We can write a computer program to write it. It's not polynomial, okay, but it's not one of these hard ones either. Great. For 25 years, people thought like this. You know, there's not a lot of problems in here, out here. Shor found two of the problems over there. Graph isomorphism, that must be there too. Guess what? People spend 25 years looking for it, and despite 25 years search, there is no known quantum algorithm that solves the graph isomorphism problem in polynomial time. So even in the place where we found other quantum algorithms, and we thought, oh, here's another problem, it must be there also, we can't find it. So that's what I'm saying. There's a lack of quantum algorithms. We know quantum algorithms here is not important because we can do these things with a regular computer pretty quickly. Quantum algorithms up here probably don't exist. Okay, polynomial algorithms. Some of them here we found, some we didn't. But there's not many. Okay. Okay, so let's sum up. Ready? Quantum algorithms use superposition and entanglement. I didn't show really how entanglement works, but how it uses in the algorithm, but they do, to solve problems. There are some amazing quantum algorithms. There are some amazing quantum algorithms that solve problems in polynomial time. There are not as many as we would like. A quantum algorithm for polynomial problems is, this is that green thing. A quantum algorithm for polynomial problems is not that interesting. If I have a computer that can sort things in n log n, and I get a quantum computer that sorts them in n log n over 2 or something like that, that's not really such a great speed up. If you have a polynomial thing, doing it even quicker is not such a great speed up. So that's not interesting. And by the way, we have to manipulate these quantum gates just like we manipulate these gates. And so it might not be that the quantum manipulating is faster than what we can do here. So that's not interesting. There probably do not exist polynomial time quantum algorithms for NP-complete problems. I'm being fuzzy here because there is a result. It's a theoretical result, which kind of, many people say it means that there are no NP-complete, there are no polynomial algorithms for an NP-complete problem. There are no quantum polynomial algorithms, but I don't know about it. Next, there are some interesting polynomial time quantum algorithms for NP problems. That's the yellow region that we were talking about, that are not complete. But there are not so many such problems. There's very few of those. That yellow region didn't have a lot of problems. And we don't have quantum algorithms for all of these problems. That yellow region, I showed you, there's one there, graph isomorphism, and everyone thought, oh, yeah, well, let's find a quantum algorithm. Didn't find it. Okay, next. There is a formidable physics engineering challenge to create large-scale quantum computers. They will probably get there. Engineers are very good. They'll probably get there. And when they do, RSA will be useless. But there are other harder problems than factoring that will be used to get computational security. In other words, you will be able to get it, don't worry. We focused on another, less discussed. You don't see this. You know, every single day you turn on your computer, there's oh, we got quantum computers can do this and they can do that. I'm sorry, this is the following. They'll be able to do this, and we're going to have machine learning and quantum computers and deep learning and it's a lot of buzz. Whatever, not saying it's false, but yeah, I'm saying it's false. Okay, we focused on another less discussed problem. Not the problem of making a large-scale quantum computer, but the lack of quantum algorithms. This doesn't seem to be a lot of quantum algorithms. This problem is more fundamental. The future is unfathomable. And that's what makes this topic so fascinating. Okay. want to point out, there's this thing called Shtetl Optimize. It's the blog of Scott Aronson. He spends a lot of time talking about these things. Why haven't more quantum algorithms been found? That's a paper by the leader of the field. Okay? Quantum Computer for Computer Scientists, that's this book. It's a very good book. I also brought a lot of copies, and you're welcome to borrow. I have this paper called An Introduction to Quantum Computing, which goes through a lot of these, which goes through, very carefully. And if you don't have it here, don't worry, it's on my webpage also. And I also have this other little paper. I also have this book, and I have this paper called On the Mysterious Aspects of Quantum Mechanics. Not about quantum computing, but quantum mechanics. And the purpose is to show that all the mystery of quantum mechanics follows from one statement. And I'd just like to read you the statement. Ready? The outcome of an experiment depends on the whole setup of the experiment. The whole setup of the experiment. Every single part of the experiment. Okay, and I get like 10 different weird things about quantum mechanics, and I show it's all from that single sentence. I have the word whole in italics, boldface, and underline. Okay, and what do I mean by whole is exactly the whole thing. Anyways, but I never published this, and I would love to get criticism or comments or something.
Listen, that one I'll read.
Oh, finally. Jay, after all these years. Anyway, so I'm not running around. My attention deficit disorder is kicking in, but I'm not running home, and I'll gladly talk to anybody. Oh, questions or anything like that?
I'll gladly get back to you about
Sounds good. Anybody? Any questions? Any unhappy? Please.
Sure, I have questions. First, thanks. There have been, I think just this past year, a couple examples of actually like regressions in what sort of quantum algorithms we have. Like a couple of quantum algorithms that we found polynomial time classical solutions for. I don't remember offhand what they were, but like I was wondering.
There's something about solving linear algebra equations that somebody has sent me. I don't know. And also this thing with, there's D-wave, which is a whole different way of talking about quantum computing. I'm not saying it's wrong or right. I don't see any I don't see clear algorithms of what these things can do. Okay, I see, oh, if we could do this, then we could do that. If we could do this, but I don't see it. I could be wrong.
Do you mean for the coming up with polynomial?
Right. When I say right, I mean polynomial algorithms to do something that a classical computer cannot do in polynomial algorithms. I don't see that. But again, I don't spend my whole life.
I mean, I know that there were a couple examples this year of people coming up with classical algorithms, polynomial time, that can also do some quantum algorithm. And then the other thing I wanted to ask is, I think you probably answered this, but if I want to classically simulate a quantum computer, and I'm okay with using 2 to the n bits for an n-qubit computer, I can totally do that, right?
Right.
Do I need some kind of random number generator or something like that for the measurements that I'm taking? Or like,
if you believe that quantum mechanics is all random, then yes. If you believe in hidden variables, then no. You can use whatever, you can use your random number generator.
okay, but so, I mean, let's say I want a Turing machine. There's no random seeds or anything. Is there a Turing machine with 2 to the n states or whatever that is exactly equivalent to, that can do, just carrying out, I don't know, Shor's algorithm or whatever?
You have to read this book, because here I talk about a quantum Turing machine, and it deals with...
But I'm talking about, can I get a classical Turing machine
to simulate
a quantum computer?
Yes. Okay. And the way to say that is BQP, which is what can be done by a quantum computer, is in NP. So there's a theorem that says that, there's a theorem, it goes to Bennett, it says that anything that a quantum computer can do can be done also by a classical computer also.
Right.
Okay, but now that it's said and everyone agrees to it, I'd like to tell you something that might not be able to do it. For example, okay, let's say I had a quantum computer, and I have a piece of radioactive kryptonite here, okay? And so classically, I can't tell if my Geiger counter is going to beep or not beep, right? because it's random. Right? But let's say my quantum computer is somehow entangled with my piece, and I will be able to, then I might be able to tell, using my quantum computer, whether or not my Geiger count is going to beep or not. Okay. That's my own example. I don't know if it's true.
I think that's similar to the kind of problem I have in mind, that quantum computers can act as perfect random number generators, I guess. And a Turing machine, you don't normally think of it as being able to produce out of thin air. So how does that interact with the BQP theorem?
Right. I don't know. But let's do another thing. Let's assume that quantum is not really random and there are hidden variables. So the whole thing is deterministic. Anyways, I don't know. Please.
So how would you know if there's an error? You mentioned that in the diagram of the gates and so on, that in between, in the two states,
right.
sorry, in the input and output, in between, there should be no measurement.
Right.
Otherwise there's a collapse.
Right.
How would you know if it has happened or not happened?
Right. Very odd. In other words, I would have to do it a few times to do that. I want to just add to the problem. Well, make it an easier problem. Where you hit, I don't know if you came late. The two boxes with the two particles, right? So I send one particle to this side of the world. I send one particle to that side of the world. Okay, and I open this side, and I see, oh, it's spinning positively.
Sure.
Well, how do I know it's spinning positively now? I mean, I see it spinning positively, but maybe somebody opened it up in between.
What?
Somebody
Opened which?
Oh, you weren't here in the beginning.
I'm sorry.
Take one particle with no spin.
Yeah,
Split it into
split.
two particles that are super.
Right.
Put one particle
Sure.
over there, one particle over there, send them
Okay.
across the universe.
Sure.
Now, the person who opens the particle here sees it spinning positively, let's say.
Sure.
How does he know that he's seeing it spinning, and he collapsed it? Maybe it collapsed somewhere in between. Okay? It's a very hard problem. Okay? It's not a simple problem. Okay? Now, you had mentioned the word error, so there's a whole thing called quantum error correction. Okay? And that's much more important than classical error correction, because most of the time this computer doesn't make a mistake, but quantum, there's a bigger chance for something to make a mistake. And so we have to worry about that a lot more. Go.
Let me just say, it was a terrible problem before they figured out how to get around the actual errors. If you read George Dyson is a historian, and he's written on the history of big canoes on the West Coast 1,000 years ago. He's also written two wonderful books on the history of the computer. And there are many, these aren't the only books. There are hundreds, thousands, more. Yeah, it's the reason you don't have very many errors in there. Actually, I found a memory error last night in one of my machines. I was shocked. The reason is because it's got a bunch of error correcting stuff. The question is, how much, as you said, how much error correcting stuff do you need? And that's the thing. I mean, yeah, that's, this is, how many years? 1945 they began to build what we recognize as regular computers.
And when they said bug, they meant a real bug. Anyways, more questions?
Can I ask another one?
Please.
So I'm in the space of using complexity theory for mapping, say, social science problems and so on. So these are inherently highly multivariate problems. Could a quantum computer be helpful?
At the moment, it's not. Could they? If you read a lot of the hype, the answer is yes. Okay? I just don't see it that, maybe you know more, I don't see it right now.
This would amount to, would superposing all your variables help with the kind of thing you're trying to do?
Well, I'm trying to understand if there's a correlation with that kind of problem and the TSP. Perhaps?
Yeah. I have to say, I spent like 2 or 3 hours looking through other presentations on the web and papers about the future of quantum computing and the future of this, and Forbes magazine has every single episode, every single issue has something about the future, whatever. And business people are really into this.
Yeah.
I just don't see a lot. I have to tell you,
Probably like expert systems.
well, we have expert
and it
systems.
never went anywhere.
Right, but there are some, like, machine learning now is really taking over, so taking off, and that's a real, right.
But it's 50
But
years
that's,
before it started.
Right.
It's 50 years after it started.
right, so it's only now. But I have a friend who works in Wall Street, and he's doing some machine learning, this and that, risk analyst, whatever. And I asked him, I said, do your bosses really invest money based on what the computer tells them to do at the end, you know, the machine learning? And he was like, of course not. You know? So I said, so why are you spending so much effort doing this? And he said as follows, he says, the people who invest in our company, they read the documents, we have to say, oh, we're using machine learning to do this, and we're using quantum computing to the latest sub-development on da-da-da-da-da. And so we have to write that, but no, we don't take it seriously. No, that's nonsense. The problem is there's a lot of money involved here, because people think, and so there's a lot of hype and there's a lot of push. I'm not saying it's false, but I'm saying it's not there yet.
It's early, yeah. And also for climate change, you know, models.
Right, so that's another thing. But right now we're modeling climate change on a regular classical.
So in that case, it's question, yes, would a quantum system be good at modeling a particular classical system?
Yeah.
And I don't see it yet. Well, first of all, for sure, as of now, they can't do it simply because they don't have the large-scale quantum computer. But again, I don't see the algorithm so much. I'm not, you know, a damper. I don't think that people should stop studying quantum computing. I just think it's just not there yet.
So your analysis is based on algorithms, but what about, you know, agent-based modeling, which is, the algorithmic part of it is minimal.
Right.
It's really a state change, and it's an emergence of patterns from very little algorithms, very, very small.
Right. Well, the whole thing about machine learning, I mean, there's stuff there. I mean,
Yeah.
I can no, seriously, you can. I play with, you know, you can do text by talking.
Yes.
It recognizes my speech very nicely, and 5 years ago it didn't.
That's right.
And so you can really see machine learning really does work, and that's
Machine
probably
learning is just pattern matching.
right.
That's all it is. Well, sorry, not only, but it has a large portion, sorry.
To me, machine learning is advanced linear algebra. It's a lot of just really great linear algebra. But go.
Thank you.
And now you're doing complex linear algebra.
No, what? Quantum computers. On the advertisement, I said all you have to know is how to multiply two complex matrices. That's it. This book. No, let me just tell you this book for a second. Chapter 1 is, and it's the most sold quantum computing book around.
Good.
But Chapter 1 is about complex numbers. Chapter 2 is about linear algebra with complex entries. And every one of those boxes can be represented by a matrix, and that's it. It's all complex numbers. It's not hard at all. It's really doable.
Yeah, like this is like Hilbert spaces, or how far does this get on the?
I mentioned Hilbert space, but even Hilbert space is not mentioned. It's just a complex vector space. Hilbert space.
The good part about quantum computing coming to the popular mind is you're not bothered by the ridiculous Hilbert spaces.
Anyways, everything is finite dimensional, so it's all Hilbert space. Okay, we're finished.